Today I want to show you a simple example of multi-agent reinforcement learning. In MARL, we use a technique called SelfPlay to train agents, enabling them to either cooperate to achieve a shared goal optimally, or compete and push each other to improve. In this video, we'll explore the competitive side. The scenario, the classic game of tag, but it's going to be one-on-one tag. If you've never seen competitive tag, it's incredibly entertaining. Check out World Chase Tag on YouTube. Now we need to create the simulation environment for the tag game so that we can train the agents. But it's going to be 1,000 times less awesome than what you just saw. In fact, we'll just use old school print statements to visualize the game. It's version 0.1, so yeah, there's a lot more room for improvements in the future. And we won't have obstacles either. So we're going to keep things real basic and focus on the reinforcement learning elements. If you haven't created a reinforcement learning environment before, I encourage you to watch my video on how to create a single agent environment. Otherwise, some of the things that I mentioned in the video might not make sense, so check that one out first. The arena is going to be represented by a grid of 8 by 8. 8 is totally arbitrary. You can make a bigger or smaller grid. The tagger and the runner are going to be dropped onto the grid randomly in each episode. They're going to move one cell at a time, and we're just going to do lateral and up and down movements, not even diagonal yet. So our action space is going to be of size 4, represented by 4 numbers, 0, 1, 2, and 3. They're going to map to these actions, up, down, left, and right. For the observation space, we just need to know the coordinate of where the tagger is and where the runner is. So this is just going to be 4 numbers in tagger X position, tagger's Y position, the runner's X position, and the runner's Y position. When we talk about training, we're essentially training a neural network, something that looks like this. The number of nodes is configurable, and the number of layers is also configurable. So I'll just draw something to illustrate what's happening. Now the input is going to be the observation space. Since we have 4 numbers here, it's going to be 4 nodes. It's going to be hooked up to the rest of the layers, of course. So we have our position of the tagger and the position of the runner. Now the output of the network is going to be a single number, so 1 node, and that's going to be the action space. So it's going to be a number between 0 to 4, and that's the output. We can use the same architecture to train both the tagger and the runner. We just need 2 instances of this model, one to train the tagger and the other one to train the runner. We haven't talked about the winning condition yet. Obviously, if the tagger is able to catch the runner, it wins. And if the runner is able to stay away from the tagger for a certain number of steps, it wins. So unlike the world of tag, we don't have a clock. We'll just use the number of steps that the runner survives as the limit. So since it's an 8 by 8 grid, I'll just do 8 times 8, 64 steps. If the runner survives for 64 steps, the episode ends and a new game starts. Now let's talk about the reward system. We'll start with the tagger first. To incentivize the tagger to catch the runner as quickly as possible, we can do something like this. We can do a -1 penalty every step that the tagger takes. And then when the tagger is able to catch the runner, we do a +64 reward. This should be enough to incentivize the tagger. Now for the runner, we can do the opposite. We can do a +1 reward for every step that it survives. and then a -64 penalty for when it gets caught. Now that we have all the reinforcement learning elements in place, we can talk about how self-play training is going to work. We talked about using the same neural network architecture, but create two instances of it. One instance of the model we're going to use to train the tagger, and then another instance of the model we're going to use to train the runner. When we first start training, we're going to drop the tagger and runner onto the grid. They don't know what to do yet. They don't know what the objectives are. So they're just going to move around randomly. Now, naturally, the tagger is going to be at a disadvantage because it's easier for the runner to reach the limit of 64 and get the big reward. Much easier than the tagger because the tagger needs to randomly catch the runner in order to get its big reward. So because of that disadvantage, we'll start training with the tagger model first. We're going to train it for a certain number of episodes, and that number of episodes is something that you can adjust. After training the tagger model for a certain number of episodes, we'll switch over, we'll load up the runner model, and we're going to train it against the tagger model that is hopefully a little bit smarter than before. After training the runner model for a certain number of episodes, you guessed it, we'll switch back to the tagger model, pit it against the runner model, and of course, we're going to go back and forth like this until you are satisfied with the training results. Yeah, so it is that simple. Something to keep in mind is that during training, you don't want one model to be too much smarter than the other model. For instance, when you train the tagger model, if it gets trained to a point where it can hunt down the runner very, very quickly, then when you switch over to the runner model will never be able to get away and get its reward, so it will never get trained. This is similar to having a beginner chess player play against somebody that's really good. If the beginner can never win, then he or she will never learn which moves are good or bad because they always lose. So keep that balance in mind. Ideally, both models will improve incrementally upon each other. Now we're ready to transform this environment into code, but before I jump into the code, I want to remind you that my code is shared on github.com/johnnycode8. My code is free to you, and so is the information in this video. So all I ask is a thumbs up if this is useful to you, and maybe share this video. Okay, jumping over to VS Code. We're going to go over this code at a high level. I'm going to focus on the multi-agent concepts. If you want to understand what each line is doing, install something like GitHub Copilot or another AI coding agent, and it will help you understand what code is actually doing. For us, we will just focus on more of the high-level concept. When we create this environment, we need to code it according to the gym environment interface. We import the Gymnasium libraries up here. You can probably install Gymnasium with pip install Gymnasium. If that doesn't work, I have a video on how to install it. Especially if you're on Windows, it's harder. We're going to use NumPy to represent the grid. Now, in the init function, this is where I'm defining the grid size and the max number of steps before the runner gets away. We're using this environment to train both the runner and the tagger, so I need a flag to distinguish which one I'm training at the moment. When it's true, I'm training the tagger. When it's false, I'm training the runner. Down here, I'm defining the action space as a discrete 4, which means it's 4 discrete numbers from 0 to 3. The observation space, as we had talked about, are 4 numbers, the X and Y position of the taggers and the runner. So it's a size of 4, and we create a box type. If you want to know more about how box works, I got a video that's maybe 2-3 minutes. Check that out. I need a variable to pass in my opponent's model. So when I'm training the tagger, I need the runner's model and vice versa. I need to pass in the model externally with this function. When I reset the environment, I'm basically dropping the tagger and the runner randomly onto the grid, and that's exactly what the reset function is doing. The get observation function, all it's returning are these 4 numbers. The move agent function, this is just some basic math calculation on moving the 2 agents around on the grid. Before the step function, let's finish up with the calculate function. Calculate reward, this is consistent with what we discussed here, how the rewards work. Now let's hop back up to the step function. Let's say I'm training the tagger. In the step function, I'm passing in the action of the tagger. So this first block applies to the tagger. I'm going to be executing the tagger's action in a moment. Here I'm trying to get the opponent's action. If I have a model passed in, I'm going to use that model to generate the opponent's action. At the beginning of training, I wouldn't have a model passed in. At that point, I'm going to generate a random action with the sample function. If I was training the runner, I'm just going to do the opposite. The opponent model would be the tagger model, and we're doing the exact same thing. We're generating the tagger's action with the model that was passed in. We're also generating a random move if the model is not present. Now that we have the actions for both agents, we're just going to move both agents on the grid. This is to check if both agents are in the same cell. If they are, that means the tagger has made a tag or that the runner has been caught. Calculate the reward at that point and determine if we should terminate this episode if a tag has been made or the max number of steps has been reached, and then return. Okay, so that is the environment. And if you did watch my video on the single agent environment, this is not that much different. Let's keep going. I have a function to print this grid. Okay, it's just math, nothing special there. The train function. Now this is important. In the train function, this is where we're doing this back and forth pattern between the tagger and the runner. At the beginning of the train function, I'm using this code to try to load existing models. You can see here on the left that I already have a trained model for the runner and the tagger. If these two exist, then try to load them. By loading the models, it makes it possible to continue training even after stopping. Now we get into the training loop. We start by training the tagger. Here we're creating 8 instances of the environment. Depending on how many cores you have on your computer, you can change this number around. If I have a runner model, I'm gonna set that as my opponent. Here I'm trying to figure out if I should start a fresh model if I don't already have one, or continue training. Now I call the learn function, and this is where all the training happens. Notice that between creation of a model and training it, it's just 2 lines. This is actually enabled by the Stable Baselines 3 library. If you don't know Stable Baselines 3, I have a video on that too. Make sure to check that out. Okay, going back down, this is where we were. So we trained the tagger model, and now down here we're going to switch to the runner model. You can see that the code is nearly identical to the top. Create 8 instances of the environment. Here I'm saying train tagger equal to false, meaning I'm going to train the runner. I'm setting the opponent model as the tagger model. I'm going to create a new model if I don't already have one, or I'm going to continue training. And again, I'm going to call the learn function on the runner model to do the training. So now this is going to go back and forth depending on how many rounds was set. And after all that training is done, we're going to call the save function. The save function is going to save a new zip file, or it's going to update these 2 zip files. After training, we can call the test function. Test function is fairly simple. All we're doing is loading the two models and then calling the evaluate function. Down here in the evaluate function, I'm creating a single instance of the environment, and I'm just gonna evaluate from the point of view of the tagger. Since whatever the performance of the tagger is, the runner's performance is just the opposite. So we just need to look at it from one point of view. I'm setting the opponent model as the runner model. And then in the loop here, where we set the environment, we'll use the tagger model to generate an action, and then we'll execute that action. When we execute this action, since we already set the opponent model up above, both the tagger and the runner are going to execute its actions. And then all we're doing is just some code to print out who did what and print out what you see here. And finally, at the very bottom in the main, you can uncomment the train function, run it. I ran it already, and that's how I got these two models here. And then you can call the test function, and it's gonna load these two models and run it. Now it's gonna do printouts, and the render frames per second controls how fast the printout happens. Let me slow this down to a little bit. It's gonna look like a wall of scrolling text, so I'm gonna edit the video a little bit to see if we can make it look a little bit better. The tagger and runner are randomly dropped on the grid, and they're pretty close together. Both of them are running to the right, and now they're heading towards the bottom right. The next step ends the game. They both ran into the same spot. That was probably the most simple multi-agent reinforcement learning tutorial on YouTube. What do you want to see in version 0.2? This is where you can influence the direction of this series. I'll try to do whatever the majority says within reason. And if there are not much views or comments, then I probably won't continue this series. So you guys decide the fate of this series.